Okay, you go with the count quiz first. Okay, let's go. Not bad. So molecular weight of antibody is 150. Quite easy to memorize. So later I will show you each part of those molecular weight. IgG, immunoglobulin G is the most common one. That is a monomer. My question was which is not monomer. In antibody sets, how many other antibody kinds?
5.
5. So among those 5, the other 3 here, immunoglobulin G, E, D, those are monomers. So one Y shape. Immunoglobulin A is more than monomer. Anybody knows how many?
Pentamer.
So, Sejan, say
5.
again.
It's pentamer.
Nope. IgA is a dimer, which has a 2 motif connected together like this. Two antibodies. Pentamer, 5 or more, is IgA. So IgM is the pentamer. And each of those monomers, molecular weight is approximately 150. This is a little disappointing. These numbers were shown in the video you have studied. How many disulfide bonds in antibody?
4.
It's 4. One pair is reduced and it exposes 2 system motif. If it's because it is a 4 disulfide bond, if you reduce them all, you open up A site, and those A site can be modified with a drug. Okay, this one has been covered by the video material. Okay, at least antibody is made by B cells. Okay. Oops, answer is wrong. Answer is a hybridoma cell. B cell is also necessary, but B cell can make polyclonal antibody. Each B cell make a monoclonal, but B cell itself cannot make monoclonal antibody because B cell cannot live for long. So to make monoclonal antibody, you make a fusion cell between B cell and cancer cell, so-called myeloma. Those fused cell is called as hybridoma cells. So hybridoma cell can live for long, and it can make a colony. It can make a cloned cells, and hybridoma cell is a keyword for monoclonal antibody. Okay, very good. So epitope is the binding site of antibody. That means epitope is on antigen. Okay, on the antigen, antibody can recognize the different positions, and the binding site of antibody on antigen, that is epitope. And what is the partner of epitope? What is the binding site of antibody? Epitope is on antigen. Then what is the other side on antibody? What do you call? That is called as paratope. Okay. Paratope binds to epitope. Hmm. If you inject antibody from horse and inject into the human, very interestingly, it may have a little, the fever may formed, but not serious immune response occurred right away. That's why you may have heard the story about the serum therapy. It's a passive vaccination. If you generate some antibody against coronavirus from other animal, and you can extract those serum, and you can inject that serum into the human, then it doesn't make very strong immune response in the beginning, but it can attack coronavirus. This kind of approach is called as a 혈장 치료 or serum therapy. Has been done for a long time, but it has some chance it may generate some immune response. That's why it's not very common. But if it is really emergency case, usually still you can use these animal antibodies. In this case, why do you think they use a horse, not mouse? It's a very simple reason.
It's more effective.
No? Effectiveness may be similar. Horse is bigger than mouse. That's why you can extract a lot of serum. You may have heard some of those story from Yonsei University, Yonsei Hospital. They extracted the serum from patient, and they injected the serum into another patient, and then they got some therapeutic effect. Okay? In that case, the problem is effectiveness is good, the problem is the amount. How much of those antibody you can extract? Horse is much bigger than mouse, much bigger than human, so you can extract a lot of horse serums. That's why horse was quite common, the animal source, or you can use maybe the cow. You can inject a horse antibody one time to human, but you cannot use that again, because once you inject horse antibody into the human, now it is antigen. It takes about 2 weeks to generate antibody. The first time that response is small, so it's like a vaccine. But second time, if you inject after 1 month, now our body is immunized against that, the horse antibody. Now antibody response is occurs right away. Now it can be very dangerous situation. Okay, that's why that kind of emergency therapy can be used only one time. Then what can be other options? You need to get injection maybe 5 times. You already used the horse antibody one time. Then what can be other option?
Use other animals.
Yeah, you can use other animal. Maybe number 1 horse, number 2 cow, number 3 sheep. Kind of a big animals you can take on. Then maybe you can use those. Still this is difficult. Hey, you can inject a horse antibody to human. Then if you inject a human antibody to human, maybe the immune response may be very, very small. It may have a small immune response, but 99% of human antibodies, they are same structure. Okay, so if you need to use the antibody as a drug, if possible, you want to use human antibody, not animal antibodies. Okay, so on Thursday, we are going to hear about this, the antibody drugs. If you want to use this antibody multiple times, definitely you cannot use animal antibody. Okay, it should be very similar to human antibody, which has a very low immune response. Okay, that's very important point. One time can be tolerated, but multiple time it cannot be. And this kind of a vaccination, using directly adding antibody is kind of immune therapy, but you use the antibody to attack directly the pathogen. Then if this is a vaccine, then this is not active vaccine. This is a passive vaccine, because you are not generating immune response and attack. You just inject already prepared antibody to attack the pathogen. Okay, that's why this is called as a passive vaccinations. Very good. Our gene number is between 20,000 to 30,000. After modification, it can be higher, but if you count those gene number from the DNA, okay, that's about 20,000 to 30,000 numbers. That's all we have. Only information we can provide to our offsprings. We have only 20,000 genes, but one person can generate more than 1 million different kinds of antibodies. So this is there is some trick. Protein should be made out of antibodies, protein should be made out of DNA information, gene. Our gene number is only 20,000, but we can generate more than 1 million different kinds of antibodies. Then what can be the tricks? That's the key part of what you need to understand for the antibodies. You may think you know about the antibody, but some of those details, this is quite unique chance you need to study seriously. Okay, antibody part is not easy. Immune is not easy. It's very complicated. Not to be confused. You should spend more time. Seems like you didn't look up the video very carefully. I strongly recommend that you look up again. Try to understand. There are a lot of information there. Try to understand as much as possible. Okay, even though we take antibody is a huge, like a million numbers of antibodies there, but that does not mean that antibody can be generated for any kind of antigen. Some antigens can raise antibody, and some people has a strong response to antigen, and some people they don't. Okay. Okay, let's move on.
Professor, I think we have one more question at cloud.
Sorry, could you say a little louder?
In our cloud site, there is one more question left in.
I know.
Or
I just skipped one.
Oh, sorry.
That's okay. You had a keen eyes. Yeah, that's true. Last question I just saved for the class. Okay, so I put up you guys put up some questions like this. The many of you answered yourself. Now here is the first question for the vaccine. The question is, somehow vaccine and antibody should be made in the level of DNA. How vaccine can make a change in the sequence of B cells of DNA? That's a very good question. And this is the key part to understand how those antibody generations. Immune system, antibody is a one part, but it's an important part. So we start with the antibody. And immune system is two kinds. One is innate form, and the other one is the adapted form. Innate form is just a blocking against randomly all bacteria or all viruses, general attack, or just the enzymes to break out. Now, specific antigen, we want to have a specific treatment. That's adaptive immune, and antibody is representative of that adaptive immune. Now, for that, some of you gave the good questions. This is given by the Sejin Sanbe. Okay, there is a D, V, D, J, and different kind of information are all on DNA. And there are some strong affinity ones, they can be selected. This is the key part. And let me summarize again. Now here, in our body, you may have studied about this. So here, this is a heavy chain, this is a light chain. Can you give the answer for this question to Kakaobang? The fastest one will get credit. How many antibodies this person can generate? Just type the number. I didn't get any answer yet.
Professor,
Yep.
I think the screen is not coming out in a full scale.
Is it? Is it okay now?
Yes.
Okay. Now here are two questions. One is, how many different antibodies can be generated by this person? Second question is, how many different genes this person has for antibody generation? Hey, come on, is that difficult? Okay, then let me explain. Now, in our body, on the DNA, okay, those genes are, every cell has this kind of a gene cluster. Now here, some numbers of genes. This is a coding heavy chain. Heavy chain is a protein, and this part is constant part here. So this is only one here. Now there are many options, 51 of these V's, and 27 of this D, and 6 of this J. Now, if I ask you how many genes are here, then you add up 51 plus 27 plus 6. That's kind of genes here. Altogether, this is maybe 80, 90, so less than 100 genes. These genes are coding antibodies. But when they make antibody, they do not use them all. They just choose one out of here and choose 1D here, 1J here, and they make these combinations. The combined one. This is one part of this heavy chain. Now, the different combination number is multiplication of this 51 multiplied by 27 and multiplied by 6. And altogether, this gives you about 8,000 different combinations. So that means this is B cell gene, or every cell in our body, we have all the same gene like this. Now, B cell matures, then B cell does not make all of this 8,000. One B cell, they choose randomly one out of each here, and then they make their identity using these combinations. That means 8,000 of different B cells can be generated. One B cell can make only one type of antibody. Now here the magic is, even though the total number of genes is less than 100, by using this combination or combinatorial function, they can generate a lot of different possibilities. That's the magic part of the immune system. That's how using our total gene number is only 20,000. It's a very limited number. But utilizing about 100 genes, we can generate a lot of different kind of antibodies. Not only this part. Now, light chain. Antibodies is this shape. This is a heavy chain. This is a light chain. Light chain also has this kind of combinations. Heavy chain has a 3 part. So 3-dimensional library. Light chain has a 2-dimensional library. It's smaller but this one is a 40, and this is a 5. It can generate 200 different kinds of light chains. That's not all. They can be combined together. Any option of a heavy chain come here and light chain come here. You can multiply this together. Then total number of this antibody is 1.6 million. Okay. Now, how many genes we used? All add up these guys, about 80, and then about 40. All together, maybe 120. Just utilizing 120 genes or 120 different kind of information, and just multiply by the combinatorial the method, and it can generate a lot of combinations. This is a trick. This is the trick of the immune system. Utilizing limited information, they generate a lot of repertoire, generate a lot of different kinds of antibody they can generate. Okay. Again, one B cell along line they differentiate or the matured, they choose only one kind. So that means one B cell can generate only one kind of antibodies like this. Okay. This is all, maybe not, because we have two sets of this gene. We have one set of gene from father and the other set from mother. Okay. Now, if you consider these two, now can you calculate how many total numbers of the antibody we can generate? This time I tried to make simpler number. Can you give the answer? Okay, very good. Takjun, how many can you get from father side?
Oh, I just add up together. From father's side, 5 million.
5 million from this side. Mother side,
Also 5 million.
it's also 5 million. Now, next question is, should we multiply those 5 million by my 5 million, or you just add up?
Add up.
You just add? Why?
Because
That's an interesting question, isn't it? Let's just say we have two sets of genes. One gene is from mother side. The other gene is from father side. Now the question is, each fragment, they can be fully combined between these two, or just it makes one set here and then separate set from here. That is a question, right? If it's a full combination, any options, one from father, one from mother, then the combination number should be 5 million multiplied by 5 million. That's even much bigger number than these million numbers, right? So it seems like from one cell, of course, it has two genes, one from mother, one from father, but they choose only one to activate. The other one is not activated. So that's why it's not full combination. That's why each of them, this is 5 million and this is 5 million. Total number is just add up this. So maybe we have about 10 million different kinds of antibody we can generate. Okay. Now, the missing question I gave you, the Juan pointed out, was my antibody gene set the same with my mother's. What do you think? Or my antibody genes are same with my brother's. What do you think?
Not exactly same.
It's not exactly the same. It's a different because there is a still combination between my mother has a 2 sets from my grandfather, grandmother. Okay, my brother has a good chance he may have same gene with me, but still there is some combinations we can expect between father and mother. At least the father has a 2 sets, mother has a 2 sets, and there can be some combinations too, right? So that's why now we can say that everybody has a different kind of antibody sets depending on the gene they have. So that's why some people has a stronger immune, some people has a better response to the coronavirus, some people cannot generate the proper antibody against coronavirus. So that's a genetic impact. Okay. There are the millions here. Million already is a quite big number, but sometimes a million is not big enough. And at least there's several more like this. I think you ever seen those 5 different kind of heavy chain, and immunoglobulin G, A came from these heavy chains. At least there are 5 different kind of heavy chains. Now, can you read this?
Alpha.
Alpha is matching to English alphabet
Immunoglobulin
A. So alpha can make immunoglobulin A. This one?
Delta.
Delta is matching to
D.
D, immunoglobulin D, IgD. This one?
Epsilon.
Epsilon matching to
E.
E. This one? Next?
Gamma.
Gamma is matching to
G.
G. This is IgG, immunoglobulin G, most common one. And last one?
Mu.
Mu is matching to
M.
M. So these 5 generate 5 different kinds of antibodies. The constant part is different. And which one was non-monomer?
A and M.
A and M. A is
Dimer.
dimer 2. M is
Pentamer.
pentamer. It's looks like a star shape. Okay, pentamer. So this is another kind of 5 different combinations. Now, if you have 1 million, now we can say 5 million different combinations can happen. Okay. Now this question was given, and generate any type of antibody against any kind of antigen. I said it's not possible. Then in that case, how can we handle those problems? If some antigen invaded our body, and then we cannot generate the proper antibody out of these millions we inherited from our parents, then what can be the other option? Still, we have some other extension of the diversity. The first set of antibody we got, that is called as a germline antibody. Germline means it's a precursor cells to make the all of our body. The precursor cells for the making these antibodies. Now, those million numbers we counted from father and mother, those gene number is germline antibody numbers. This is our starting point. Once they start to differentiate, and then they recognize against some antigen, and they are pre-selected. If they recognize some antigen, then they can be activated, and they proliferate quickly, and then they make more numbers. Okay, out of million, you choose maybe 1,000 of the best antibodies first. And then those antibodies, those B cells, they go to so-called somatic hypermutation. They have only one set of antibody, right? They already selected Hey guys, are you there?
Yes, we can hear your
Yes.
voice.
Yes.
Okay.
Yes.
Yeah, sorry. Seems like the connection is not stable today. Everybody's here. It's okay. Everybody's here. Do you see this screen?
Yes.
Okay. So let me repeat this part. So the numbers of antibody we just counted, those numbers are inherited from our parents. They are called as germline antibodies. They are billions. So our starting point is a million antibody. That's not all. Through those mutations, once they are selected to be activated, then they generate a lot of point mutations until they reach stronger and stronger binder. Okay, so million here, and then each of them can generate thousands, then multiplied together. Now you can expect altogether we may have billions of different combinations. Okay, that's the power of this combinatorial the antibody, and also through these hypermutations. Now there is interesting the two model. You may have heard these two models for enzyme and substrate binding. So when enzyme protein bind to small molecules, there are two kinds of models. One is a key and lock. Key is small and lock is big. So key may be ligand, lock is a receptor, or lock is an enzyme and key is a substrate. Or induced fit. In the beginning, they don't bind to each other very well. But by changing their conformations, they bind like this by changing those conformation and fit better. Okay, these two model was competing for a long time. And when they compared this germline antibody versus somatic hypermutation, the matured one, seems like a germline antibody is fitting to induced fit. In the beginning, those germline antibody is flexible. So that's why it can bind many different kind of things, but affinity is a little low. When they start to bind to the antigen, and then they fix those different positions by hypermutation, and they make those antibody more and more rigid and rigid. They cannot move much, but their binding affinity to the antigen becomes stronger and stronger. Okay, through hypermutations, the model is changing into chain lock model. That means that antibody, original germline antibody, is less specific. They can bind many different kinds of things. But through point mutations, this matured antibody, they can be more and more specific and selective, and binding constant is higher and higher. Okay, that's what is going on during those maturation of those antibodies. This process takes about 2 weeks in our body. Once we get antigen in our body, then they start to send out the germline antibody, select first the binders, and then mature those antibody into specific one, and then multiply those numbers, and then conquer the whole body. That takes about 2 weeks of time. That is what we call vaccinations. Okay. Now, this is the general shape of antibody. Now, as you can see here, so here, this is a one big one, and exactly the same one, blue one here. So this is a one heavy chain. This is another heavy chain, one light chain, one light chain. Okay. So if you think about this symmetry, and this symmetry is what kind of a symmetry here? Is that mirror image, or this is rotational image, rotational symmetry?
Rotational.
It cannot be mirror.
Mm,
Should it be rotational? Cannot be mirror image.
I don't exactly know.
Well, some of you may currently studying the organic chemistry, and you guys may have learned about the chiral phenomena, mirror image. The component of this antibody is amino acid. Amino acid can be either the enantiomer, either D form or L form. But in nature, we have only L form amino acid. Then this side and this side, they look very similar, but they are not mirror image. That's why this is C2 rotational symmetry it has. Okay, anyway, this heavy chain and this heavy chain identical. This light chain, identical. And if you look at here, this is so-called immunoglobulin. Molecular weight is about 150 kilodalton. And this is very easy to memorize because whole structure here is almost 1/3, 1/3, 1/3. Okay? If everything is 150 kilodalton, then this part, this side, this part can be
50.
50. This part,
50.
this part,
50.
and one heavy chain.
50.
One heavy chain can be 50. Yes, one heavy chain can be 50. One light chain,
25.
25. Okay, it's quite easy to memorize, isn't it? Similar to the size of a virus, bacteria, and human cell, right? Each of them is about 50, and half of this is 25. Okay, heavy chain is about 50, light chain is about 25. Now, if you look at those structure, usually they use this kind of the scheme. And as you can see here, those the connection of light chain and heavy chain through this disulfide bond. And this kind of a disulfide bond, 1, 2, 3, 4. That's why if you utilize these positions to add the drug, then you reduce this part, means open up SH, and it can generate 8 different positions. Problem is, once you reduce this part, binding of this heavy chain to this light chain, it becomes very weak. There's a good chance that these two motifs can be dissociated. Okay. Anyway, total position of a sulfide bond site is sulfur site is 8, and this surface SH, are they nucleophile or electrophile?
Electrophile.
Chance is a half and half, and I already told you this last time, guys. In our body, we don't have much. You don't have much electrophile. We have a lot of nucleophile. Nucleophile means nucleophile. Phile is like. Nuclear is a nucleus, right? That means nucleus-like component is electron-rich component. Okay, that's why OH, hydroxyl group, NH, nitrogen, and SH, sulfur, they are good nucleophiles. Okay, let me repeat. In our body, we don't have many electrophiles. The natural molecules, natural products, we have a lot of nucleophile. That's why to make a covalent binding, we need to add electrophiles. Okay. Now here, let's look at this part. half of this heavy chain and half of the light chain. This part is called as FAB, fragment antigen binding. This half, this is called FC. What can be C? Fragment. Can you guess?
Constant.
Constant. Yeah, good guess. Originally, this C was a crystallizable. Crystallizable means this sequence is exactly the same. That's why they are repeating same structure. But this FAB, this part is a constant, but this part is changing depending on those antigen shape. That's why this part is difficult to crystallize because different antibody has a different structure here. So originally this part was called FC. This C was crystallizable, but it's the same meaning of a constant. Okay. So up to here, this is constant. Heavy chain, this is a heavy chain. Light chain, this is a light chain. And this part, half of this part is still constant. And upper half, this is antigen binding site. Okay, this site is called as a paratope. Paratope is a part of antibody. Okay, and then this part is the hinge region. So what did I say? Pattern of this paratope in antigen?
Epitope.
It is epitope. Okay, epitope binds to paratope. These are partners to each other. Okay. So if you inject one antigen into the body, only one antigen, then how many antibody can you get, you think? You inject just one antigen. How many different kind of antibody can you get? Answer is either one or many.
Many.
Why many?
Because for only one antigen, there should be only one paratope, but the rest side of the antibody could be many.
Can you make the answer using epitope rather than paratope?
I mean, one antigen can have more than one epitope.
If this is an antigen, it can be epitope here, epitope here, epitope here. Different antibody can recognize different part of this antigen. That's why even though you inject just a single antigen, still it can generate hundreds of thousands or maybe millions of different antibodies. Okay, so that's why you need to have one specific antibody, just a single one. That's what we call monoclonal antibody. If it's a mixture, then it's difficult to analyze the data. Okay, those mixtures we call polyclonal antibody. So if you just inject antigen, let's say there is coronavirus infected patient and cured. If you take their blood, serum, in their blood, in their serum, there should be many different kinds of antibodies. That's a polyclonal antibody. So that's why when I said inject a whole serum or cure the person's serum, that is not monoclonal antibody. It's a mixtures of many different kinds of polyclonal antibodies. That's a serum therapy. That's a 혈당 치료법. Means there's a lot of uncertainty there. There can be some of them can be potentially toxic. Some of them can be contaminated. Some antibody may behave funny, attack some other important part. So that's why to make into classified the drug, it should be single antibody, so-called monoclonal antibody. Okay. Now, if you look at this antibody structure, which part is important? This part may help, but this is not. This is a constant part, may not be necessary. Even this part may not be necessary. If you wanted to make the antibody small and small, the most important part is this part, isn't it? If you just focus on this part, what can be the size of this part? Come on. Altogether, this is 150.
Smaller than 25 kilodalton.
It's about 25. We can approximately can say, right? So this is 1/3, and then half of it, this is about 25. So that's why if you look at those antibody structure, you can make many different the fragment. So this is the whole structure, and then half of the 1/3 over here, and then even make it smaller, only this part here. Now, one is from heavy chain, one is from light chain. Those are two peptides, and that's difficult to make. So that's why by connecting one side here and then connect it to the other side, all together 1/3 over here, this is called as FAB, antigen binding fragment. And upper part here, this is called as FV, fragment of variation. And then if you connect this side, this N terminal to C terminal here, this is now becoming single chain, one peptide. Okay, that means if you inject this 25 kilodalton size of information as a DNA, it can generate one protein connected like this. So this is quite convenient antibody-like material. Size is about 25 kilodalton, and this is a single chain, and this is mimicking antibody. This is so-called SCFV. As you can imagine, this is a very important and useful tools. Okay, so if possible, rather than handling all together this big antibody, maybe focusing on this small one would be very nice. Now, antibody, original antibody is this side and this side exactly the same. It's a C2 symmetric. Now, sometimes now we can make one binding site and the other binding site is different. To do this, we need to make this one and make this one and then combine them together. So this is kind of asymmetric, artificial antibody. Then we can do one binding and another binding and can do something. This is an artificial one. Okay, there is some engineering for binding site of antibody. As you can see here, different options of combining different part and different motif, removing some part is possible. Okay. Well, how the light chain was attached to the heavy chain? So good answer was given by your friend. They can be synthesized separately. Okay, so one is a heavy chain, one is a light chain, and they recognize themselves, and they're connected by disulfide bond, kind of a self-assembly. So inside the one cell, heavy chain is synthesized, light chain is synthesized, and in protein level, they combine it together. Okay. Yeah, first the video is that during the maturation of the T cells, and only 25% of the T cells survived. Okay, this is a good chance to talk about T cells. T cell, antibody is made by B cell, right? So B cells, sometimes they have secreting antibody, but before they secrete antibody, B cell has this antibody is attached onto the membrane. It's kind of receptor. Okay, B cell is here. So during those B cell maturations, they choose only one binding site, and then after matured, they started to cleave here and then secrete these antibodies. So B cell has a combinatorial receptor, right? By the way, B cell's receptor can be secreted, but T cell also has a similar structure like this. Not two of them, one of them like this. This is a T cell receptor. And very similar to antibodies, T cell also has a combination on this part, and it can generate many numbers of up to 1 million different kinds of T cell receptors. But they do not secrete. Receptor is bound on the cell membrane. Now, B cell and T cell is very similar to each other, right? B cell is just secreting those binding partner, and then they go out and then bind to that binding site. T cell carries this receptor and then recognize the enemy, and then the cell itself is a weapon. The cell is secreting toxic chemical material to kill the enemies. Other than that, B cell function and T cell function through these receptors very similar. That's important. Okay, that means their maturation step is also very similar. In the beginning, they have millions of different combinations to bind to something, right? Then there is some selection part. Immune response is recognizing self or non-self. If it is a non-self, they recognize its enemy. Then these immune cells, the antibody or these T cell receptors, they should not attack ourselves, correct? That's why in the beginning, when they mature, they circulate in the body and then try to recognize our own body. There's two sets of maturations, selections. First set is they need to recognize something. If they do not recognize anything, then they are not immune cells. So this is positive selection. Non-functional cells die out in the beginning. They don't bind to anything, then they die out. Then we lose half of them. Second selection is if they bind very strongly to our cells, any material, any molecule generated by our cells, then those cells should not be activated. If they are activated, they will attack our cells, correct? So that's why the second selection is negative selection. And if they recognize anything in our body, they die through apoptosis. Okay? Then first half, they died because they don't do anything. They don't bind to anything. That's why they died. Second selection, they bind too strongly to our own cell, our own molecule. Then half of them died. Only 25% left over. They do not bind to our cells very strongly. And now, if there's any new things that come into our body, now they start to react to those material. That number is so-called here, 25% survived. Is it okay, Taekjun? So this question was given by Taekjun or Taekjun? Was it your question?
Yes, me, yes.
Okay.
Thank you.
So this is kind of a maturation of the process. That process is almost the same for B cell and T cells. Okay. If we have wounds, then some cells, they secrete the signaling molecules. How do they announce location of the infection? Any idea? We got some infection on the finger, let's just say. And some cells in that area, dendritic cell or helper cells, they secrete some signals. And they try to recruit more immune cells to that area. What can be the mechanism?
Cytokines.
Cytokine. What is a cytokine? Cytokines is cyto. What is the cyto? Cyto means a cell. Yeah, cyto means a cell. Kine means it's a signaling molecule. Cytokine means it's kind of a targeting cell hormones or signaling molecules. Cytokine can be one possibility, or maybe simple one is you can just generate some inflammation material. Then that area becomes swollen. If they are swollen, then maybe the blood vessels become loose. Then circulating cells, they have a better chance to penetrate through the blood vessels. Then they can collect more immune cells. It's also possible stories. So it can be either cytokine directly binding to other cells, or maybe environmental change around there. Okay. Yeah, later part, there's a sweeping antibody and recycling antibody. It's very similar idea to each other. If you have an antibody binding to the target cell, then outside is a neutral. And then this small vesicle inside here, they are acidic environment, go in, and in acidic environment, they can be released. So you can modify this antibody's binding. Neutral, they can bind. Acidic, it can release. Then it can be, this released part, this can be degraded. And this part, they can be recycled to go up. And then this is recycling. If one antibody can be recycled, then maybe they can do the same job multiple times, maybe more efficient. Sweeping is almost a similar idea, but they modified further of this part. In the beginning, when they bind to on cell surface, previously it was endocytosis should happen. It may take a little longer time. But now they have a chance to bind to this receptor here directly and modified this part. And then they can be recycled much quicker. That's why this kind of enzyme is called as sweeping, kind of cleaning out. Okay, just a small changes. Now this kind of a small techniques in the book I recommended, Bioscience 이해. There's a lot of examples there. So I strongly recommend you finish those reading of those books. And there are many techniques and small changes and change and develop further and further. There are small modifications on over and over. There's a never-ending story. Okay. Important thing is what kind of idea is introduced further and further. Okay. Bispecific, it can be very sterically strained, maybe. But there's a good answers given by Tekjun. Target molecule may be small, antigen epitope may be small. That's why antibody binding to site may not be very tight. Maybe okay. Now phage display. Phage display case, there's a good answers was given by Sejin Sanbae. And here the term was used. Single chain fragment of a variable region. Okay. So this week I didn't give you any assignment. Next week assignment, if you like, then this can be one good topic. Utilizing this SCCFV and phage display can be good topic you can choose and present. Phage display is mimicking antibody generation, but much easier. And last year they got the Nobel Prize in this field in chemistry. And this is quite important and also interesting the topic. So this is so-called biopanning or molecular evolution and antibody-like strategy. So I would recommend one of you may take this topic and be interesting in the presentations. Okay. By the way, the question was, there was only one example I could find, and then, I found at least 9 out there. This is very good, but better is you may want to have a reference here. Okay, if you want to say something unique information to support your claim, it's better to have solid reference. Now, this question I gave you, rather than just using primary antibody and then label each of them, maybe straightforward. Why do you want to use secondary antibody? Well, some standard answers is like, if it's a primary antibody, if you just label directly, maybe the function is affected. That assumption is maybe the fluorescence molecule is bound to FAB or FV, the paratop site. If a drug molecule or fluorescence molecule bind to paratop, then it can block those functions. Or secondary antibody can increase the sensitivity. Original primary one, you can label only one. Secondary, you can get multiple. But if you think about the symmetry of the antibody structure, how many secondary antibody can bind to primary antibody, do you think? Secondary antibody should bind to FAB or FC.
FAB.
FAB is an antigen binding site. If a secondary antibody binds to FAB, is that good?
No, I don't think so.
Then it should bind to the FC, right? Then it is on the tail side. Secondary antibody does not bother with the primary antibody's original function, correct? Then if it's binding to the FC site, reasonably, how many binding sites do you expect they have? It's a C2 symmetry, so most likely it's a 2. It has a 1 heavy chain and the other heavy chain, most likely 2. Expecting binding a 4 is very difficult. So that's why, even though that increased the sensitivity, maybe double, just twice, may not be 10 times. Really important part is this part. By utilizing the primary antibody, and then if you use a secondary antibody, if you should label primary antibody one by one, it's a lot of work. You need to have primary antibody prepared, and then label one by one. Sometimes it's very difficult, or the efficiency is very low. If you use the secondary antibody can recognize once the primary antibody is generated by, let's say, mouse. The secondary antibody, you can just use only one. Mouse antibody, anti-mouse antibody targeting FC. Then you can make a lot of combinations again. Those secondary antibodies you can label with the different colors. And now you have 100 primary antibody. You just need only one secondary antibody. Still, you can detect each of them. So not only those cost issues, this is more flexibility issues. Okay. So there are a little more similar answers like this. Second part, cross applications. Now here you can choose primary antibody source of animal, and then same numbers of a secondary antibody. If a primary antibody is a mouse antibody, horse antibody, dog antibody, then you can just use secondary antibody against the mouse, against the dog, against the horse. Then you can use the different combinations. So then you can have another multiplexing or multi-labeling. Multiplexing means this is a combinatorial approach. You have multiple numbers of a primary antibody, multiple numbers of a secondary antibody. You can use different combinations. Okay, any questions so far about the immune system? Okay. Now one at the top I want to give you. Sudden blotting. Anybody knows what this means? Nobody knows?
Is kind of experimental method to find the specific DNA sequence in
Okay.
DNA samples.
Finding specific DNA sequence. That's what he said. So if you run the gel, if you break up the cell and run the gel, there are a lot of DNAs here. Now you want to know the specific sequence is there or not. Okay. The technique is, if you run DNA sample, there are a lot of them, then you choose those sequence and make complementary sequence. Complementary sequence after you run the gel, this is like a chromatography. Complementary sequence if you run, then they can recognize, okay, here and here, this is my interest of genes. This is utilizing the hybridization of a double strand, complementary sequence binding. Okay. Then using this, you can find specific sequence out of this mixture of many different genes, DNAs. Okay. This technique is developed by this person, Dr. Sutton. Okay. So that's why this technique is called as a Sutton blotting. Blotting usually means after chromatographic separation and then detecting your target materials. That's a blotting. Okay. Sudden blotting is a DNA sequence-specific DNA detection. That's a sudden blotting. Now, DNA can bind to RNA. RNA can bind to another RNA too, if those sequences are complementary, right? So exactly same technique has been applied to RNA. Now, can you guess what is the technique name? That name is from this name. If DNA was a sudden blotting, if somebody did similar experiment with RNA, what do you guess?
Western blot.
No,
Northern blot.
northern blotting. If RNA technique is a northern blotting, funny, right? And then similar techniques, if you run proteins here, and then recognize your target protein by antibody, that technique is called as a Western blotting. Okay, so those three terms are fully established: northern blot, southern blotting, northern blotting, and Western blotting. Now there's a one missing part, right? Eastern blotting. So people are trying to use that term Eastern blotting here and there by using small molecule recognition, carbohydrate recognition, but that part is not fully established yet. People are still trying, but it's not fully accepted by the community. That's why that site is still open. If you find a new technique which can be really influential, then you can take those terms, Eastern blotting, as yours. Okay, maybe the time is up for now. So let's finish. I have a little more material, but let me cover next week. Okay, this week again, there is no other assignment, but please finish those reading the book Bioscience here. And next class will be on Thursday. And Thursday, the three people will present about the antibody of the drug. The last week of the assignment. And seems like the understanding or studying level for immune system, today's, I observed it's not good enough by now. Look after the video carefully, okay? And next week material would be a little more complicated. Now we are going to move into immune checkpoint. Before we learn new things, this week's video material and Bioscience book, both of them will be very important. Okay, don't left behind. So try to read those material and see you on Thursday. Any question for today's? Okay, if not, okay, if not, then let's just stop here. See you on Thursday. Okay, bye-bye.